In section 2, we look at perpendicular and angle bisectors. Now remember, the perpendicular bisector cuts the segment in half. So we had segment AB. We draw CD to be in the midpoint and perpendicular. Now the important thing in this section is to look at the special relationships that end up happening because of this. For example, if I were to draw these two sides here, since this is on the perpendicular bisector, we've already proven that by side angle side, these sides would also be congruent to each other. Basically, we get an isosceles triangle from this. So that's our first theorem. If we have a perpendicular bisector, we choose any point, whether it's high or low on that bisector, we know it will always give us an isosceles triangle. Really, we're skipping to PA is congruent to PB. On the other hand, if we have an isosceles triangle, we know the two sides are congruent, we can use that to prove that if we draw a line cutting down here, that it would, like if we make this perpendicular, it would also be the bisector, or if we cut it to the bisector, it would also be perpendicular to that. We know that this P is on that perpendicular bisector. We can also use the perpendicular bisector theorem just for solving a problem like this. Because we see we have a perpendicular bisector, okay, we have a midpoint here, and we have a right angle, we know it's a perpendicular bisector. Therefore, we know it's an isosceles triangle, and we know that 4x will be equal to 6x minus 10. So we simply solve it for x, and we get x equals 5. Now be careful, they ask for AB, so we plug that in. AB was equal to 4x. Plug in the 5, we get 20. We can also use the perpendicular bisector for a problem like this. They ask for the possible locations of a stand when we want to build it equidistant from the roller coaster and the spaceship. Okay, so here's our roller coaster over here, our spaceship chute over here. If we draw a line, if we find the midpoint, and then if we construct a perpendicular to that, that might be a little bit off, but for the sake of the problem, that's okay. So if we know that this is the perpendicular bisector, then we know that we can put this point anywhere on this line. And so we have an infinite number of points that would actually fit this problem. The next idea is defining the distance from a point to a line. Now this is important, this will come up a lot, that if we were asked about a point and how far it is from a line, we could think of a lot of ways that we could measure that distance. We could measure it from here to here to here. If we want to find how far we are from the line, we could go to any of those places. But we want to think about it as the shortest possible distance. And so the distance to a line is always going to be defined as the perpendicular to that line. And so if I want to know the distance from the sides of an angle, say from an angle bisector, so this is my bisector here, and I have any point wherever it is on that line, and I can look at the distance from that point to the sides. So if I'm going to measure the distance to the sides, remember, we need to have the perpendicular distance. And so that goes down to either side, and both of those parts can be marked as perpendicular. Now you might notice something about these. These appear to be the same length. If we measure them, we would find that. And so that's going to be our first theorem here, the angle bisector theorem. We'll be dealing with if we have an angle bisector, so this bisector is clearly marked, and we're looking at our distance. So if it's a distance, these have to be perpendicular. Therefore, we would know that these segments over here are congruent to each other. Now we would know that that's true because if you look at this, we have an angle and another angle, and by the reflexive property we have a side there, so we could prove this using angle, angle, side. Now on the one below, it's the converse of the angle bisector theorem. So notice what we have this time. We have the distance here, and we have this length here. Now we don't have a line drawn in here, but if we did draw connecting Q to S, this theorem tells us that Q to S would be the angle bisector, basically saying that these two angles would be congruent to each other. Now if we look back at this one, we'll see why. We have an angle, we have a side, but there's a right angle, and we have a reflexive property here, so we're using the hypotenuse leg theorem to prove this. Now if we're using the angle bisector theorem, what we're noticing, first of all, I have congruent angles here, which means this is an angle bisector. We're noticing the right angles, which tells us that these are the distances to the sides, which means these are congruent because they're meeting at the same point. Therefore, so angle bisector, yes. Perpendicular to the sides, yes. So we can just simply set 7x equal to 2x plus 25 and solve it for x. Notice again they ask for Rm, not x. So we'll finish this problem by finding Rm. 7 times 5 gives us 35.